Okay, let's do a couple more examples working with partial derivatives. Okay, in example 3, let f of x comma y equal the natural log of x squared plus 3y. So let's find the partial of f with respect to x and the partial derivative of f with respect to y. So just using that other notation there, where it's very important to keep track of which letter, which variable we're treating as the variable, and then the other one is a constant. So we'll write it out, the partial of f with respect to x. And so we'll just go through and we'll take the derivative of this, treating x like the variable, and we treat y like a constant. So the natural log of stuff, okay, so let's treat this like a chain rule. So the natural log of stuff, remember the derivative is 1 over the stuff times the derivative of the stuff. And so since we're taking x as the variable, the derivative is going to be 2x and then plus, and then remember, y is a constant right now. So it's plus the derivative of 3 times a constant. The derivative of a constant is just 0. Okay, and then we can go ahead and just place that 2x in the numerator there. And this will be the answer. That is the partial derivative with respect to x. Okay, now if we start over, the partial with respect to y. Okay, so same thing, the derivative of natural log of stuff is 1 over the stuff. And then times the derivative of the stuff. This time, we're letting x be a constant, so don't do the power rule on it. The derivative of x squared, if x is a constant, is just 0. Maybe I should put parentheses just to be careful there. So 0 plus, okay, and then the derivative of 3y, when we're treating y as the variable, that's going to be 3. Okay, so then we can go ahead and just place the 3 in the numerator, and this is the answer, the partial derivative with respect to y. Okay, so very important, that difference of which variable we're taking the derivative with respect to. Okay, now let's try some where we actually evaluate derivatives at different x, y values. So the notation f sub x a comma b, or the partial of f with respect to x of a comma b, that's just going to represent the value of the partial derivative when we plug in values for x and y. So when x is a and y is b. Okay, so not really anything too crazy there. We're just going to go ahead and take the derivative, the partial derivative like it says, and then after we find that partial derivative, then we plug in these numbers for the x and the y values. Okay, so for this one, the first thing I want to do is actually just find out what is the partial derivative in the first place. Okay, so just using that notation, and we're going to be switching around with the different notations a lot, but the fx with the xy, that's the notation we're using right now. So before I plug in the -1 and the 2, we want to find out what the partial derivative with respect to x is. Okay, again, very careful. That makes a huge difference of which variable we're considering. So going through, we're going to treat x like the variable and y like a constant. So 2x squared, the derivative with respect to x is 4x. Plus, okay, be real careful here, x is the variable and this y cubed and the 9, all of that is a constant. So the derivative of a constant times x is just the constant. So all of that is the constant and then the x is gone. Okay, and then plus, and then the derivative of 8y with respect to x is 0 because that's a constant, and then the derivative of the 5 is also 0 because that's a constant. Okay, so then this is 4x plus 9y cubed. All right, so now if we wanted to go fx, plugging in -1 and 2, now we just want to plug it in to this expression here. So -1 goes in for x, so it's going to be 4 times -1 plus 9 times 2 goes in for y. Okay, so that's going to be -4 plus, that's going to be 9 times 8, so 72. And we get 68. Okay, so that's the result. That is the partial derivative with respect to x evaluated at -1 for x and 2 for y. Okay, let's work with the other notation here. So this is the partial of f with respect to y evaluated at -4, -3. So first things first, let's just find the partial of f with respect to y. Okay, and so going back up here, now x is a constant. So the derivative of 2x squared is 0. Then we've got this stuff, okay, got to be a little more careful here because y is the variable. So the 9x, that's all a constant. And so the power rule of a constant times y cubed, the 3 multiplies down in the front. So that's going to be 27x. All of that is the constant. And then with the power rule, reduce the power by 1. Okay. Plus 8y. So when we're doing the derivative with respect to y, that's going to be plus 8. And then the plus 5, that's still 0 as the constant. And so this simplifies a little bit as 27xy squared plus 8. And now when we want to do the partial of f with respect to y evaluated at -4, -3, just plug in -4 for x and -3 for y. So 27 times -4 for x, -3 for y. Okay, I think I need my calculator for that one. It's going to be a little bit of a big number here. So 27 times -4 times -3 squared is 9, so times 9. And then plus 8. Overall, I got -964. Okay. Okay, part C, find all values of x and y such that both the partial derivative with respect to x of x comma y equals 0 and the partial derivative with respect to y, x comma y equals 0. Okay, so kind of interesting. First things first, we actually just need to find the partial derivative of each of them. Well, we already have those from before. So let's go ahead and write down the fx of x comma y. It's not too bad to do that over again, but we already have that one done from part A. That's 4x plus 9y cubed. So let's go ahead and go 4x plus 9y cubed. And we also had the partial with respect to y. We use the other notation with that cursive looking D thing, but same thing, partial with respect to y, we got 27. Now remember, this is where we're not plugging in anything yet. This is just the derivative itself. So 27x y squared plus 8. Okay, so those are the two partial derivatives. Okay, and we want to find values of x and y such that both of those partial derivatives equal 0. That's kind of hinting at something. Remember, a lot of times, a lot of the applications when we were finding extrema and all kinds of stuff, you're setting derivatives equal to 0. So this kind of a process has a whole lot of different applications. Okay, so how do you find out which values cause something to come out 0? Well, take these different equations, and I want to set them equal to 0. And we need to find x and y that cause that one to be 0. And then for the other one, we also need 27 xy squared plus 8. We also need that to come out 0. So what does that look like? Well, you might think that looks like a mess, but what that actually looks like is a system of equations. We have two different equations and two different unknowns, two different variables. And that means that you can solve by some kind of a substitution, okay? So there's a couple of different ways that we can do this, but I think it's probably pretty easy to solve the first equation for x, okay? This equation over here to solve for x or y, you'd end up with like some kind of a variable fraction mess. So I don't want to get a variable fraction. Just regular fractions aren't as bad as like variables in the denominator. So yeah, we need to solve, and maybe I'll make a note of that. We need to solve by substitution. Okay, and so yeah, substitution, lots of different options for what you can substitute, but I think the easiest substitution is to get x by itself in this first equation. So I'll take the 9y cubed and I'll subtract 9y cubed from both sides. And we get 4x equals negative 9y cubed, and divide both sides by 4. And here's a substitution now, negative 9y cubed over 4. Okay, so solving by substitution. I now have an expression for x, and we can plug that in to the other equation. Okay, so just pure algebra at this point. We're just solving by substitution. So in this equation, we're going to replace x with this thing. So that x right there is going to be replaced with negative 9y cubed over 4. And then there's that y squared that's also there. And plus 8 equals 0. So we're just doing a substitution. Now in this equation, the only variable is y, so we can go ahead and multiply this all out, and it looks like we can solve for y. It's going to be y to the 5th power, but then there's a lot of other constants involved, so it looks like we might be able to isolate the y to the 5th power, and then take the 5th root of both sides. Okay, so just trying to think about that a little bit in advance. So as we multiply all of this stuff out, the 27, that can go straight onto the numerator with the 9. So let's see, 27 times 9. So this is negative 243 y to the 5th power, right? Because it's cubed times squared. So that's going to add up to 5 all over 4. Okay, and then I want to try to get y by itself eventually. So let's go ahead and subtract that 8 on both sides as well. So we want to get y by itself and then eventually take the 5th root of both sides. So how do we get rid of this 243 over 4? Well, dividing by the number in front of the y sometimes throws people off a little bit. So maybe let's think about this as multiply both sides by the reciprocal. So if I multiply both sides of this equation by 4 over 243, and let's include the negative. I think this makes a little bit more sense than trying to think about dividing by a fraction. Okay, so I'm multiplying both sides of the equation by the reciprocal, and that's just going to fully cancel everything, including the negatives there. And then we have y to the 5th power equals, okay, so what happens here? So negative times negative is positive, and then 8 times 4 is going to be 32 divided by 243. Okay? So y to the 5th power, if there were other y's involved, kind of scattered around that we couldn't combine into a single term that has the y, then a 5th power might be kind of difficult to solve for. But since it's just this one location of this y to a power, yeah, we can get that y to the 5th isolated. And now we're taking the 5th root of both sides, which is the same as raising both sides to the 1/5 power. So if you wanted to use your calculator, you could do it like that, because a power re-raised to a power multiplies. And so that gives us y to the 1st power. So let me continue the work over here. So we have y equals, and so 1/5 power, that's a little bit tricky, especially if you're doing the entire fraction by itself. So what I would recommend is probably just do the numerator and denominator separately. Anytime you do a fraction raised to a power, you can apply that power to the numerator and denominator separately, which might help, because if you try to type that all into your calculator at once, it might display some weird fraction that we're not quite sure what that is. The reason why I'm doing this is I'm just noticing that this one can all be done in our heads. Okay, so the 1/5 power of 32. So again, that's the 5th root. So what number times itself 5 times is 32? That's nice, that's a 2. And then the 5th root of 243, that's also a nice one. It's actually 3, because 3 to the 5th power is 243. So the reason why I did that is no calculator needed. That one actually came out a nice number. Okay, but if you just typed in the 32 over 243 raised to the 1/5 power, I guess your calculator would have displayed 0.6666666, and maybe you would have recognized that that's 2/3. But I always like to write a nice reduced fraction if possible. Okay, not quite done yet. Don't forget that you need to plug this back in into the x form. So we need to go back to our x substitution, and we need to plug in y equals 2/3, and then we'll be done. Okay, so if we plug in y equals 2/3, it's going to be -9 times, and we're plugging in 2/3 for y. And then simplify this in a few steps. So that will be like -9 times cubing each part, top and bottom separately. 2 cubed is 8, and then 3 cubed is 27. And so to clean that up a little bit, let's see, 9 times 8/27, that reduces to 8/3. Okay, and it's still a little bit tricky because that's all over 4. So the way that I like to think about this is we can actually flip and multiply this by 4/1. So flip and multiply. And that just helps me out so that I can think about how to do this, because it looks weird if it's a fraction divided by a number. So this is going to be, that reduces a little bit. So the 2 and 1. And so the overall answer for x is going to be -2/3. So that one was definitely a little bit more fun. Or maybe we have different definitions of fun. But yeah, pretty interesting. We found all values of x and y such that both derivatives with respect to the different variables equals 0. And it caused a system of equations, and we were able to solve by substitution. And we got that y is 2/3, that does the job, and x is -2/3. And those together, those do the job of making sure that both partial derivatives come out 0 when we use those numbers for x and y in the partial derivatives. Okay, cool stuff. I'll make another video to pick up on tangent lines, rate of change, and applications.